Hello everyone, welcome back. We are talking about U-substitution for calculus, and in this particular video we're going to do problems that are definite integrals. So in the first video we talked about how to do U-sub where we were indefinite integrals, so we were actually finding a general expression for it. In this actual problems, these problems we're going to do today, we're actually going to find a value. We actually want to know what the total change on the interval from 0 to 1 is of your function. Now, I'll tell you guys before we continue that you can always do Math 9 and plug this into your graphing calculator to actually verify that your answer is correct. So over here is kind of the steps that we talked about in the first video where we have two functions, right? We have an x and we have an x squared plus 1 all raised or all cubed. So when you look at what could be u, well, there's two questions that you should ask yourself. And the first one is the derivative of 1 also there? Well, the derivative of x squared plus 1 is actually 2x. So again, if we don't really care about the constant, because we can easily pull that out, we do have that derivative. The other question you could ask yourself is one of the functions raised to a power? And so the answer to both those questions is yes for x squared plus 1. So we can already say that the u is going to be x squared plus 1. As we get further in this course and you may choose the wrong u and you may work on it and then realize that's not right and then go back and try something else. So these questions are just kind of strategies to figure out which one's better for us to do. Now, if we implicitly differentiate this, so I went ahead and I talked about this one time in the previous video and I'm going to do it again here. So if we go ahead and take the derivative of this implicitly, we get du over dx, just like we would get dy over dx for that. And this is going to be 2x dx dx, right? To 2x dx dx. And so the 2x dx's are actually just going to cancel out, so we don't really care about that. And then what's going to end up happening, ladies and gentlemen, is that we're going to cross multiply. We're going to cross multiply, and we're going to get du is equal to 2x dx. So you can see that we have the x and we have the dx. So we have to get rid of the 2. So we're going to divide both sides by 2. So now dx, x dx is equal to 1/2 du. So when I go ahead and start subbing into my integral, I can go ahead and say that again, I'm going to go ahead and pull a constant out because we've already talked about this before in the previous video. So the 1/2 goes away, and so this x and this dx ends up just being du. So I can go ahead and get rid of that because du is equal to that. And I don't know why I wrote that so atrociously. That's even a word. So du. So now we know what u is. U is x squared plus 1, so I can go ahead and do u cubed. So this is what we did in the first video, right? We were able to now take all of this stuff and be able to rewrite it in terms of u. So the only additional step that we actually have here is our integrals. We want to change our interval from 0 to 1, because remember, these are x terms. So this is x equals 0, this is x equals 1, and we want to find out what they would be for u. So just like in the previous video, I talked about my bridge step, this is a connection between u and x. So I can easily see that when x is equal to 0, so we're going to look at this bottom one right here first, when x is equal to 0, I can do 0 squared plus 1. So u is going to end up being 1. When I plug 1 into my function, so I get 1 squared is 1, 1 plus 1 is 2, I get that u is 2. Once you've done this, your new problem is right here. And it's a much easier problem to do because we're just now integrating u cubed. So once you find the answer to this, then you've also found the answer to this. These are equal to each other. These are absolutely equal to each other. So I'm going to go ahead and get rid of that and just say that, again, these two are the same answer. So this integral is equal to this integral. And that's what's beautiful about this problem. So I can go ahead and put a 1 here and a 2 here. So all we have to do now is solve. So we get a 1/2. We're going to integrate u cubed, which is going to be u to the 4 over 4. And we're going to evaluate that from 1 to 2. So there's no plus c here, ladies and gentlemen. This is literally just going to find our intervals, and then we're going to evaluate from 2 to 1. One of the things that I personally like to do before I continue on is I've got a 1/4. This can be written as 1/4 u to the 4th. So I'm going to go ahead and pull out the 1. So go ahead and pull that out. And then I'm going to go ahead and be left with u to the 4th, evaluated from 1 to 2. So eventually we're going to have a 1/8 here. So I'll multiply the 1/4 and the 1/2. I'm now going to plug in 2. I'm going to get 2 to the 4th minus 1 to the 4th. So f of b minus f of a goes back to the fundamental theorem of calculus. So 2 to the fourth is going to be 16, minus 1 to the fourth is 15, so I get 15 over 8. And so this answer is 15 over 8. All right, so hopefully that's helpful for you guys. The only extra step, again, is to convert for x's to u. So let's move on to another question and see what we can do with that one. So I shifted through the packet here, and we're doing example number 10, but it's the one that's further in the packet, where I want to integrate from 0 to 3 of x times the square root of 9 minus x squared dx. And we did one very similar to this in the first video, so we're going to go ahead and say that u is going to be equal to 9 minus x squared, again because the derivative is right there, minus the constant, and the fact that this is underneath the radical. And so immediately we're going to write du, we're going to take this derivative, so it's going to be negative 2x dx, and then we have an x and a dx, so we need to get rid of the negative 1/2. So I'm going to go ahead and pull out the negative 1/2. And so I know this is very similar to the other examples, but something happens in this example, and I want you guys to see what's going on with it, which I like. So let's go ahead and start subbing in. So we're going to go ahead and pull up the negative 1/2. And so right here, what I do is I want to go ahead and say, okay, when x is equal to 0. So again, I'm looking right here, this function right here. When x is equal to 0, what is the u going to be? So when x is equal to 0, I get u equals 9 minus 0, which is going to be 9. And then when x is equal to 3, then I plug in 3 here. I get 9 minus 3 squared, which is 9 minus 9, which is going to be 0. And then we know that x dx, this right here, is going to be our du. So we can go ahead and do that. And then we just are left with the square root of u. We're left with the square root of u. All right. So when we do the problem, notice that our upper bound is actually less than our lower bound. You can still do it this way. This is still fine. You can still do the fundamental theorem of calculus. You can still do f of b minus f of a, and that's totally fine. But we already have a negative out here, right? So why not make our problem easier and just flip our integral, and that way our sign now comes positive. And remember, we do not do any flipping of our function. So this is still going to be the square root of u du in our problem. And now, once we've done that, we have now a positive answer here, so that's awesome, and we have our bounds. But again, you can do f of b minus f of a. It's always going to work out in the end as far as our signs are concerned. So I'm going to go ahead and do 1/2. I'm going to integrate this. Remember, this is u to the 1/2 power. So I'm going to do u to the 3/2 power, and again, I'm going to pull out the 2/3, and I'm going to evaluate this from 0 to 9. From 0 to 9. So when I do the problem here, the 2's are going to cancel out, and so I'm going to go ahead and be left with 1/3. And I'm left with u to the 3/2 evaluated from 9 to 0. 9 to 0. So when I start plugging in here, I'm going to get 9 cubed. Actually, it's easier for us to do 9 squared, I think. So without a calculator, 9 squared is 3. 3 cubed is going to be 27. And then I'm going to go ahead and plug in 0. Well, 0 raised to any power is 0. So this answer is going to be 27 over 3. Which is going to end up giving us the answer of 9. Okay, so this answer will be 9. So again, ladies and gentlemen, the only other step that we've done from the first indifferent integrals is the fact that we have to change our bounds, and then now this is our brand new problem, right? This is our brand new problem, and then we actually are getting a value instead of a plus c. Okay, so let's do one more example for the definite integrals. So question number 13 says 0 to 1 of f of x dx is equal to 8/3, and 0 to 5 of f of x dx equals 15. Find the following. So the first one, a, is not even worth really discussing. Notice that the only difference is that on this first integral right here, we've just switched 0 and 1, right? We flip-flopped them. So you guys know that if I were to take a negative out, I could then have the same thing back. Right, and we already know what this value is. We know this value is going to be 8/3. So a is simply going to be equal to the opposite of that, or negative 8/3. So that one is pretty simple, pretty basic problem that we don't really need too much work on. But it's also a really helpful tool for us. Now, question number 5, question letter B, we're looking at 1 to 5 of f of x dx. So if we look at B, then we're going to write the property that from 0 to 5 of f of x dx, that's going to be equal to 0 to 1 of f of x dx, and this is one of the properties that you guys learned, plus 1 to 5. And I use the analogy that we're at mile marker 0 and we want to walk all the way to 5. Well, we start at 0 and we walk at 1 and we stopped, and then we continued from 1 to 5, and then we eventually got from 0 to 5. So all we have to do is plug in. We know that this is equal to 15. We know that 1 to 0 is going to be equal to 8 over 3. And then we just got to figure out what the interval from 1 to 5 of f of x dx is. So this answer is simply going to be 15 minus 8 over 3. And if we want to be more specific about, or and in an FRQ, this is completely fine. So please know that you guys can do that. 15 minus 8 over 3 is totally fine. But if we want to do it this way right here, then we're going to get that this is going to be 37. I had to think for a second on mental math, man. So there you have it with A and B. All right, A and B. And then for question number C, I don't want to spend too much time on that one, but you would just pull out the 5. You pull out the 5. So this property says, okay, yeah, we can pull that 5 out right now. And so we know that this integral right here from 0 to 1 of f of x dx is going to be equal to 8/3. So this is simply going to be 5 times 8/3. So again, totally fun answer, but 40 over 3 is also a legit answer. All right, so I'm going to erase all this and we're going to talk about D and E, which again, once I do D, then it's easy to show you E. Okay, so I'm over here now, we're going to do D. And so D is going to be from 0 to 1 of f of 5x dx. So for this particular problem, we need to use U-substitution. We don't know what f of 5x is, but we know what f of x is. So if we're going to go ahead and make u equal to 5x, again, we're going to use du is going to be equal to 5 dx. So we're going to go ahead and we don't have a 5 in here, so we're going to go ahead and pull out a 5. Du equals dx. So again, anytime you write u, you're going to always write du. You're going to take that derivative and do dx. Right now, this is our u, right? So we really don't have a 5 here. We have f u, and then our dx is equal to du. So we have to pull out a 1/5. So when we do this problem, we're going to have a 1/5. And remember, we have to change our bounds. We have to change our bounds. So and actually, I will talk about in a second what happens if you don't change your bounds, because you technically don't, but it's so much easier to do it this way. But moving forward here, we plug in 0 for x, we're still going to get u for 0. We plug in 1 for x, we're going to get 5. And then we're left with f of u du, right? So this is what it is. One of the things that we talked about is the fact that now we have the integral from 0 to 5 of the function, right, of our function, but we just changed x to u, right? It doesn't matter if I changed this 0, if we're looking at this in context of the problem, 0 to 5 of f of smiley face dx is still going to be equal to 15. It doesn't necessarily matter that this isn't as x's and these are u's. We've already changed our bounds based on the fact that now we have a u here, so these are the same function. So the point I'm making here is that this value is going to be equal to 15. Because again, we've changed our bounds to 0 to 5. And I'm going to multiply that by 1/5. So this answer for part D is going to be equal to 3. It's going to be equal to 3. And you do the exact same thing with letter E. You're going to make u equal to 5x. So again, you're going to make d equal to 5 dx. We're going to pull out a 1/5. Du equals dx. So we're going to have a 1/5. We're going to change our bounds. So when x is equal to 1, then u is going to be 5. When x is equal to 0, u is going to be 0 of f of u du. And so we're going to look at this, ladies and gentlemen, and say that this right here, I don't know why I'm writing so slanted right now, 0 to 5 is just going to be equal to -15 based on the conversation that we had in part A, right? I can flip this and make it 0 to 5 instead of 5 to 0. And it's going to be -15 times 1/5. So this is going to end up giving us a -3. Okay, -3. So those are 2 videos on U-sub for integration. And hope that makes sense, as I always say. So I will see you guys back here in the next video. Good luck.